My name is Yoshihiro Yamashita at the University of Fukui, Center for Research in Fibers and Materials. We are developing masks and clothing that can prevent coronavirus infection. There are 3 routes to coronavirus infections: through direct inhalation of large droplets of 5 micrometers, through direct inhalation of small aerosols of less than 1 micrometer, and throughout hand contact with the virus on masks and clothing surfaces. For this reason, we need to use nanofiber filters that viruses can't pass through in antiviral treatments for masks and clothing. We are simulating the design of cloth and sponge masks that are comfortable and have no gaps for viruses to enter. Biaxial tensile testing machines at the University of Fukui measure the data needed for CAE analysis. The cloth mask developed in this way has no gaps between the mask and the face. Coronaviruses can live for 1 to 2 days on a cloth surface. When we examined the survival time of SARS-CoV-2 on silk fabrics, it was 1 day as well. But when the silk was made into nanofibers, the survival time decreased to 6 hours. The polypropylene mask also kept the virus alive for 7 days. We use ethylene vinyl alcohol copolymer for our nanofibers. The diameter of the nanofibers is 100 nanometers, the same as that of the coronavirus. The large specific surface area of the nanofibers makes it easy for the virus to physically absorb. Also, the surface of the nanofibers is coated with an antiviral agent. There are 3 typical methods of antiviral treatment. The first is to apply nanoparticles of silver or copper ions to the surface of the nanofibers. Copper ions bind with moisture in the air and produce hydroxyl radicals. These radicals destroy the envelope of the coronavirus. The second method is an antiviral treatment using persimmon tannin staining. Urethane polymer and persimmon tannin are dissolved in an organic solvent and electrospun. The resulting fibers are between 400 and 700 nanometers in diameter. The antiviral effect of tannins has already been proven by Professor Sakaguchi and his colleagues at Hiroshima University. In addition to persimmon tannins, green tea tannins were also found to have similar antiviral effects. Unfortunately, there are no reports of the SARS-CoV-2 virus yet. Masks stained with persimmon tannin are already available on the market. The tannins do not destroy the viral envelope but rather inactivate the virus by cross-linking it with spikes in the virus. The third type of antiviral treatment is the application of compounds with quaternary ammonium salts at the end of the silane coupling agent to the surface of the fiber. Quaternary ammonium salts are the same components as surfactants. This silane compound is an excellent antiviral agent with excellent washing resistance due to its ability to bind strongly to the fibers. The size of the coronavirus and the diameter of the nanofibers is 100 nanometers each. Although there are gaps between the nanofibers, the coronavirus is able to physically absorb the coronavirus on the surface of the nanofibers as it moves forward in a Brownian motion. However, the gap between the melt-blown and spun-bonded nonwovens is too large for the coronavirus to be physically absorbed. Iris Oyama of Japan has adopted PVDF nanofibers made by the electrospinning method for the filter of the mask. This is the achievement of Professor Kim of Shinshu University. We have succeeded in making nanofibers from water-resistant EVOH and polyurethane emulsions. The solvents for these nanofibers are safe water and alcohol. These nanofibers have excellent water resistance. Even when immersed in water at 20 degrees Celsius for 24 hours, the fiber diameter changes by less than 10%. Professor Wang and Professor Lin of Deakin University suggested that the coil could be used in place of a nozzle. We have adopted this method for mass production of nanofibers. Large quantities of nanofibers can be spun from the Taylor cone that forms on the surface of the coil. This is an overview of the equipment we use for the lab. The voltage is 35 kilovolts and the distance between the coil and the target is 15 centimeters. We have now started manufacturing on a 1-meter wide coil. The maximum production speed is 1 meter per minute. Both sponge and cloth masks have voids that the virus can easily pass through. Therefore, the layer of nanofibers are created on the surface of these masks to prevent viruses from entering. The fiber diameter of the nanofibers in the manufacturing machine is still thick, but it is between 200 and 700 nanometers. This is a comparison of a normal non-woven filter mask and a nanofiber filter mask. The nanofiber mask was able to remove 97% of particles as small as 0.3 micrometers. However, a normal surgical mask only removed 75% of the particles. Sponge and cloth masks can only remove 35% of 2.5 micrometers particles. By creating a layer of nanofibers on the surface of the sponge or cloth mask, it is possible to remove 90% of the particles. However, 0.3 micrometers of coronavirus passes completely through an aerosol sponge mask or cloth mask. A layer of nanofibers on these surfaces can block 50% of the aerosols. Our goal is to develop a mask that can block the SARS-CoV-2 virus and not cause suffocation. Two contradictory things. Thank you for listening. Please send us a summary of your questions.